There is a shot. Oh, it's one line. Yeah. Yeah. If I was, I would ask
So we're going to take away the percenter.
No, not yet. That's and then I will be also.
Okay, I think we can start the session this afternoon. So it's my pleasure to introduce you to Samuel Greenblatt, and he will talk about exoplanet science with JWST and Roman.
Okay, great. Okay, great. Can everyone hear me okay? All right. I'm sorry to report that I don't have any musical accompaniment to go along with this presentation. So it's not going to be quite as awesome as what we just heard, but I'll do my best to keep it entertaining. All right. So for those of you who don't know me, I'm Sam Greenblatt. I'm a research scientist across the street at Johns Hopkins. And previously, I was a Kalbfleisch Fellow at the American Museum of Natural History and the Flatiron Institute in New York City. And I got my PhD at the University of Hawaii in 2019. But that's enough about me. Let's jump into exoplanets with JWST and Roman. All right. There we go. Beautiful. Okay. So as my talk title says, this is a journey through space and time. So we'll start with a journey through time here. Here we're looking at planet mass versus orbital period. As a function of time, you can see the years kind of going by there. First, we only knew about our solar system, but then in 1995, we started finding a whole bunch more of these exoplanets. Then in 2000, we found the first transiting exoplanet. And as time has gone on in the last sort of decade, you know, what we know about exoplanets has really exploded. We now know of over 4,000 planets. I think actually that counts up to like 6,000 now. And so I'll note that the colors here also correspond to different detection methods. And so I'll go through all of those except for imaging. I think that one's kind of straightforward, and you'll hear a little bit more about that in a couple talks from now. The sort of history of exoplanets starts with the radial velocity detection method. And so this is a method where basically you're looking at the wobble of a star as it's pulled back and forth as the planet orbits around the star. And this actually requires a lot of photons because you're taking spectroscopy. And so it was dominated by ground-based facilities. But then over the last decade or 15 years or so, the most planets were detected using the transit method. And as this requires precise photometry with minimal duty cycle interruption, this means that transit surveys were generally dominated by space-based facilities. And so once we discovered transiting planets, as I mentioned, the first one was discovered in the year 2000, Hubble actually gave us the first opportunities to see into planetary atmospheres. And so with the Hubble Space Telescope, we could actually observe a planet transit, but in multiple wavelengths. And so you can actually see how the star and the planet appearance changes as a function of wavelength. To show that just slightly differently, you can see on the right here, we're looking at planet radius versus wavelength. And certain atmospheric features can cause changes in the transit depth or the effective size of the planet that we see. And once the first transiting planets had been discovered, Hubble Space Telescope gave us great opportunities to actually study their atmosphere, sort of right from the start. So only 2 years after we had found the first transiting planet, we were actually able to confirm that it did in fact have an atmosphere with this not so great plot that we have here. But basically the idea is that if you look across the top, that's the transit depth as a function of wavelength. And you can see that once they had binned those wavelengths, this feature at around 589 nanometers due to sodium gave the planet a slightly different radius in that particular wavelength bin than in all of the other wavelength bins. And that told us that there was something in the planet's atmosphere, so the planet looked a little bit different in that particular wavelength due to, in this case, a sodium emission. Since then, Hubble has been really instrumental in revealing the sort of diversity of planetary atmospheres. So back in 2016, David Singh made this plot, which basically showed what we knew about exoplanets or exoplanet atmospheres at the time. And what you can see is that there are only maybe 10 or a handful of so systems, and they have different, sort of properties that you can observe in, from all of these transit spectroscopy measurements. You can see these emission features that I mentioned, also some water features in between 1 and 2 microns. There's also signs of clouds and hazes. Those are sort of the ramps that you're seeing on the left of this plot. But also point out that the data out past 1.6 microns on this plot is pretty limited. And so we haven't had too much chance, or with Hubble we didn't have too much chance to understand planetary atmospheres in the infrared. Meanwhile, transit detection has totally exploded thanks to Kepler K2 and TESS. So again, this is just showing all the planets that we knew of, I guess, in 2020. And you can see that basically below 10 Earth masses on this plot, essentially all of those yellow dots are from Kepler. And so Kepler really revolutionized our understanding of small planets with thousands of new planet discoveries. And this actually revealed new features of planet demographics. So probably the most famous is the radius gap, which is a lack of planets between 1.6 and around 2.2 Earth radii. And that's basically the boundary between rocky super-Earths and gaseous sub-Neptune worlds. And actually, with enhanced follow-up and better stellar parameters from Gaia and other sort of similar missions, we could actually get ages for these systems and show that at young ages, these sub-Neptunes seem to be a little bit more common. They're a little bit larger, but over gig-year timescales, they can actually lose their atmospheres and end up turning into these super-Earths, so that the ratio of those two types of planets becomes more similar. There we go. And this was really, transformative. Kepler really made it possible for us to determine planet occurrence rates. And these showed us that small planets are much more common than large ones, at least around main sequence stars, and that planet occurrence is roughly uniform with the log of the orbital period. And so we use this to determine that around 10 to 20% of all sun-like stars should host Earth-like planets. Which was a really exciting result. From there, we then used K2 and TESS to then extend that beyond the main sequence. And so here we're looking at just some results about planet occurrence around white dwarfs as well as red giant stars as well. And one of the things that we were able to then do is see these slight differences in planet occurrence, which then provided new insight into how planetary systems evolve. And shockingly show us that potentially planets can actually survive around white dwarfs or maybe even are reborn at these late stages of stellar evolution. We also learned about planetary atmospheres from these missions, Kepler K2 and TESS. This gave us evidence that hot gas giant planets can become inflated around their host stars over time, but also that the hottest planets around these stars were actually less inflated than we expected. Particularly at really high masses, which teaches us something about the heat and the energy transport in planetary atmospheres. And so that was great, but things have gotten kicked up a notch in the last couple of years. So JWST launched on Christmas 2021 and has been basically revolutionizing the field of exoplanet science or exoplanet atmospheres ever since. So here's just the distribution of submitted and accepted proposals for the JWST Cycle 2 General Observing Program. And you can see that exoplanets accounted for almost a third of it, actually beating out all other subcategories in fraction of accepted proposals, and almost beating galaxies in the total time allotted as well. And the JWST exoplanet results have really made quite a splash since then, so much so that they were the cover story of Nature magazine in February of this year. And with good reason. So just look at this spectrum from WASP-39b, a hot Jupiter that was observed by JWST. It's loaded with tons of spectral features that have been, listed in the colors above here that we can actually resolve into their component atomic and molecular species that cause them. And so, just for reference, I'm going to put what we had from HST overlaid at kind of a similar wavelength range. And you can see that, so the optical features, the sodium lines, we had already seen, but essentially everything redward of 1 micron was more or less brand new. And this has constrained some of the most interesting components of the planetary atmosphere. So in addition to the already detected sodium and potassium emission, JWST detected expected equilibrium features of water, carbon dioxide, carbon monoxide, and clouds at very high signal to noise. In addition, it detected this less expected disequilibrium SO2 feature right around 4 microns. Can I point with this? Yes, I can. Yeah, right here. And that feature actually indicated that photochemistry is occurring in the atmosphere of this planet. And another exciting piece of this is that the disequilibrium nature of SO2 makes it a more precise constraint on the metallicity of the planetary atmosphere than just those equilibrium species where the spectral changes are more subtle. So here's the SO2 feature versus CO2 and H2O. And so I'm really excited to see, how many more detections of disequilibrium chemistry or just unexpected chemistry James Webb is going to find in these hot Jupiters. And beyond hot Jupiter analysis, JWST can detect similar spectral features in much smaller planets. So we can search for atmospheric escape in now Neptune-sized planets as well. And that'll inform our understanding of how their atmospheres evolve over time. In the case of post-main sequence systems, for instance, the atmospheric escape of a planet that's shrinking, so this model in orange, should be measurably less than the atmosphere of a planet that's growing in size. And so that'll let us probe which of these models actually describes how these planets are evolving over time. And JWST can even go further than that. It can study the atmospheres of rocky planets. So unfortunately, no such rocky planet atmospheres have yet been found. So here I'm just showing the results from JW observations of TRAPPIST-1b and C. And unfortunately, neither one seems to be showing any signs of a thick or even Earth-like atmosphere, which can be shown by these curves near the bottom here. So most likely these are just bare rocks. But again, this is only the beginning. There are, tens more rocky planets that are already scheduled to be observed by James Webb. JWST is also transforming our ability to understand planet formation. So here's a side-by-side comparison of images of Thumbelhot, which is a young nearby A star, imaged by HST on the left and JWST on the right. And the extra level of detail in the JW image is pretty astounding. There are multiple gaps. You can see sort of a misalignment of the inner and the outer disks. And actually, there used to be potential signs of a planet in the HST data that has now been essentially ruled out. But there are new evidences of sort of these dust cloud collisions that might have been found in the James Webb data. Finally, JW can characterize planetary mass companions that have been found in nearby wide binary systems, such as this one, VHS 1256b. The spectrum of this widely separated planetary mass companion gives detections of sodium, potassium, water, carbon dioxide, carbon monoxide, methane, and silicate clouds. So there's all throughout the spectrum, even though it's hard to see here on this scale, basically all of that is signal. There's very little noise in the spectrum. And so these various features are all due to those different atomic and molecular components. And so JW is characterizing a more diverse set of planets than was ever possible before. Not only are we getting these, sort of standard hot Jupiters, but we can push all the way down to rocky planets. We can get, very young systems, very old systems. It's really powerful. But Roman is going to take this even further by detecting a larger and even more diverse group of planets than we've ever found before. And so just to sort of take everyone back to their SAT prep courses, I threw an analogy on the top of this slide where Roman is to JWST what Kepler was to HST. So Roman really is a demographics machine whose discoveries will complement the detailed follow-up possible with James Webb. And so in a number of systems with sort of sun-like stars, Roman astrometry will be able to do a whole bunch of things. We can detect orders of magnitude more brown dwarfs, more free-floating planets with Roman, an order of magnitude more transiting planets as well. We have new targets for atmospheric and coronagraphic imaging that you'll hear about in a little bit. Again, the astrometry that we'll be able to do will constrain the existence of cool gas giant planets by a factor of 5 more precisely than Gaia. Like I said, we're going to get lots and lots more planets where we can do demographics. And the key to that will basically be the Roman Galactic Bulge Time Domain Survey. So this is basically just a survey of the galactic center, so more or less like this little video is showing you. The field of view is around 2.2 square degrees. That'll be covered with a 15-minute cadence over 60 to 72-day seasons over 5 years. That means that we're going to monitor tens of millions of stars where we can detect these transit and microlensing events. And for the first time, we'll actually be sensitive to planet populations beyond 5 kiloparsecs from the sun. And to just give you an idea of, the proposed fields for that Galactic Bulge Time Domain Survey, these are going to be 7 adjacent pointings in Bada's window, the sort of clearest window near the galactic center. And, thanks to previous studies, we know that you can actually detect planets in this region of the galaxy. And the study has basically been optimized to try and produce as many gravitational microlensing events or detections as possible. And so just to talk a little bit more about how microlensing work, so microlensing planets, or planets detected through the microlensing technique, are shown by the dark blue points on this plot. And you can see that they occupy kind of a wider region of parameter space. They're at wider separations than a lot of the transiting planets, for example. And they're also at lower masses than we could probe otherwise. And part of that is because of how these microlensing events are detected. So essentially, the way that microlensing works is you have one star that passes in front of another star, and then it'll effectively lens that background star, making it increase in brightness. And then if you have another planet that's in orbit around that lens, it'll cause a secondary increase in brightness that we can actually see and measure. And so on the figure here on the right, you can sort of see what an overall light curve of a microlensing event looks like. I'm going to bring it back one more time just so everyone can see. If I can. There we go. But essentially, the entire microlensing event takes around 2 to 3 months of one star passing in front of the other. But the sort of little bump that you get on the event, so the microlensing event, you get this overall Gaussian sort of shape, but then you can see you get this little blip up here as well, and that's due to the planet. And that planet event only takes, an hour or two. And so we really need this, 15-minute cadence to characterize these events well, and also get that full 2 months of baseline so that we can see the whole microlensing event. All right, there we go. And in order to have a lot of these microlensing events occur, you need a really high stellar column density. And so the galactic bulge is the perfect place to look. So you can sort of see the crazy level of crowdedness in this simulated image here, showing 3 of the different bands that Roman will be observing in. And so this bulge survey is predicted to find approximately 1,400 planets with orbital separations from 2 to 10 AU and masses from larger than Jupiter down to Mars masses. And so this will be the first sort of survey, or large survey of planet populations that will be sensitive to solar system analogs. We could potentially detect all of the solar system planets except for Mercury, and potentially even detect some moon mass objects. I think they have Titan and Ganymede here at the bottom. And in addition to that, those are all, planets in bound systems, but the bulge survey will also be sensitive to free-floating planets. And so since we've detected so few of these objects, it's really hard to estimate exactly how many will be detected in the Roman survey. But it's predicted that we'll find between 300 to 3,000 free-floating planet events in this microlensing survey. And while the microlensing survey will be providing demographics of solar system analogs, the same data is actually going to be providing more transiting planet detections than we've had ever before. And so with 15-minute cadence of tens of millions of stars for many months, there we go, we'll be able to detect 60 to 200,000 transiting planets around a wide range of stellar types and planet sizes. That's more than an order of magnitude of the number of planets that we know of today. And so also the number of planets detected is actually heavily dependent on the metallicity dependence of planet occurrence within the bulge. And so this study will also provide a detailed probe of the dependence of planet occurrence on stellar metallicity, particularly toward the bulge. And just to show this in a slightly different way, here's the expected distance distributions for the different size planets on the left, different stellar types in the middle, and different regions of the galaxy on the right. And so not only will this survey find tens of thousands of planets in the galactic bulge, but it'll also find planets on the far side of the galaxy. In addition, most of the small planets that it finds will be within 5 kiloparsecs of us, which makes follow-up with telescopes like JWST feasible. And so here's just the combined expected yield of the Roman galactic bulge time domain survey from transits and microlensing. And so this will allow us to both detect solar system analogs as well as provide an order of magnitude more planets than we've ever detected before. So this bulge survey is really going to revolutionize exoplanet science. But that's not the only revolutionary exoplanet science that Roman can give us. It can also test planet occurrence rates in globular clusters, which have largely been forgotten due to some of the failures of previous studies. But the huge field of view of Roman means that it can image an entire cluster all at once. And now our knowledge of occurrence rates and trends from Kepler mean that we can basically step up our globular cluster survey game. We can better choose which clusters to look at. And if it works, there's lots of potential for additional studies for planets and clusters with both JWST and the Roman general astrophysics surveys. And so within just a couple of degrees of the proposed galactic bulge survey fields, additional Roman pointings could cover all of few of the most metal-rich and therefore best potential planet host globular clusters in our galaxy. And so here I've highlighted the globular clusters that are nearest to the galactic center, and specifically labeled those clusters with metallicities greater than -0.2. One of those clusters is less than 2 degrees away and could capture both the metal-rich cluster and a more typical globular cluster at -1 metallicity within the same Roman pointing. And thanks to previous surveys with ground-based telescopes, with a pixel scale 3 times larger than Roman and a limiting magnitude around 3 magnitudes fainter, they found 34,000 stars, which was the same number as the previous failed surveys of globular clusters. And they found that many stars among these 2 most metal-rich clusters that I've highlighted in the galactic bulge. And so if we can observe these clusters, even at half or 1/4 the cadence of the rest of the bulge fields, and even for 1 season instead of 6, that's still almost 10 times the baseline of this previous survey. And that makes planet detections 3 times more likely. Not mentioning that the Roman RMS will be better, we'll have probably more stars, and they'll actually be close to solar metallicity. And so taking that all together, 1 season of time domain observations of one of these metal-rich globular clusters can actually determine whether planet occurrence in these globular clusters versus the Kepler field are inconsistent at a greater than 3 sigma level for the first time. So I think this should be really exciting, and yeah, I think it would be a great thing for Roman to look at. In other in the other core community surveys, Roman is also going to be doing some exoplanet science. So for example, the JWST passage survey is predicted to detect tens of thousands of brown dwarfs within a few kiloparsec. But with Roman, they're going to survey, 100 times the amount of sky, and so they're going to increase this yield to millions of brown dwarfs in the high latitude wide area survey. And the high latitude time domain surveys should detect these things out to, again, 5 kiloparsecs or more. We can also detect things like dusty or polluted white dwarfs in these surveys, and so start to understand the sort of final stages of planet evolution. In addition, another survey that's been proposed for Roman to do to better understand exoplanets is the TEMPO survey. This is a survey predicted to find around 150 exoplanets that are less than 10 million years old, and a similar number of exosatellites. So these would be sort of sub-Earth-sized objects that are orbiting brown dwarfs or free-floating planets in the Orion nebula cluster. And this would be a great thing that JWST could then build on. You could use JW to image the most interesting or the most obscured sources that are found in the survey. In addition, we could revisit other globular clusters. Clusters like 47 Tuc or NGC 6752, which are much more metal poor than the clusters I was previously mentioning. They're so large that hundreds of thousands of individual stars could be observed. And that should allow for a constraint on planet occurrence in these, very metal poor regimes. And it could reveal differences between globular clusters related to their unique chemical abundance patterns. And so the old ages of these clusters, too, would also inform planet occurrence as a function of time. And so you can imagine connecting this with something like the TEMPO survey, you can really see how planet occurrence changes as a function of age. And so in summary, both JWST and Roman will rapidly expand our knowledge of the diversity of planetary systems. And while JW does this in a wide range of these nearby planetary systems, Roman is going to expand its reach halfway across our galaxy, detecting planets in ways that could never be done with such large numbers before. And so together, JW and Roman will put planet demographics in a galactic context. Thanks for listening, and I'll take your questions now.
Thank you. Do we have questions online already? Then let's start from the live audience.
Hi there. Thanks. Great talk. Could you talk a little bit more about how you plan to detect free-floating planets that are not bound to their stars? I don't work on exoplanets, and so when that just seems a little bit impossible to me.
So it is not impossible. So basically, the idea is you're looking for these same sort of microlensing events. But just imagine now that instead of having, a lens source as well as an extra blip on top of it, that instead you only have one sort of underlying event, but it's due to something that's planet mass. And so basically, when you detect these free-floating planets, you're getting the same sort of Gaussian-like curve, just the amplitude is smaller because the free-floating planet is smaller. But again, that depends on the sort of, geometric interaction. And so you can actually detect these free-floating low-mass objects.
Do you have other questions from the audience? Yeah.
Thank you. Great talk. My question is, I didn't follow quite well how you concatenate microlensing with transits. So can you talk a little about?
Sure. Yeah. So what I will say is that the detections of microlensing and transits will be completely different. But the idea is that using the same data set, you can do both sets of these studies. And so essentially by taking 15-minute cadence of these, very stellar rich fields, for these sorts of 2 to 3 month seasons, you can both detect these microlensing events, but also for all of those stars, you'll get a light curve where you can sort of detect a transit event in sort of the typical transit approach. And so using these same data sets, you're actually getting, by analyzing sort of different light curves, you can get both these microlensing planets and these transiting systems in the same data set.
Okay, got it. Thanks.
Do we have any question online? You have one in the room here?
Do we know why there is this gap in planet size? It's not detected. I believe you said between 1.4 Earths and 2 point something. Why is there a theoretical reason for the difference between solid and gas? Or?
Yeah, so that's basically exactly it. So this has to do with how planets form, and so essentially, if a planet, planetary core, doesn't reach a certain mass, it's never going to be able to accrete gas from its surroundings, and so it stays sort of limited at this, sort of slightly larger than Earth size, but it's still basically a rocky planet. But basically, once you get to a mass that's sort of like between 10 and 30 Earth masses, this is not super, I'm not an expert on this, but basically once you get to a higher mass, then you can actually start to accrete the gas in the protoplanetary disk that's around that planetary core. And so that lets you turn, what would be sort of a 2 Earth radius planet into something that's larger, like 2 or 3 Earth radii. Then there are other processes over time that can then evaporate the planet's atmosphere and move it back to being a rocky planet. But basically, you don't always have that happen. It depends on how close you are to the host star and things like that. And so you end up with this sort of dichotomy of planets where you see these 2 peaks with this gap in between at around 2 Earth radii.
Question.
Excellent, great talk. I was curious, I'm very interested in finding more brown dwarfs, or free-floating planets, as you call them. I'm curious about how are we going to find masses for the free-floating planets? Are we going to find dynamical masses, or masses times, sin I or some other factor that's going to be really annoying to disentangle? Because all brown dwarfs, you can assume they're the same radius, so this will be really interesting to get densities.
Yeah, so for free-floating planets, I think basically we'll get some sort of mass ratio, but that will also depend on, again, like the geometric transit probability. And so it's going to be really difficult to get masses for a lot of those objects. We can estimate it, again, from the sort of like the amplitude of the microlensing effect, but it is going to be really difficult to get masses. And so we would require some sort of follow-up. So something like JW could then, you could imagine you do sort of image of all of the star, or some subset of the stars within the galactic bulge, and so you can get like an overall stellar mass range or radius range. But I think for individual systems, it's going to be pretty difficult. We're going to be limited to sort of these population level analyses of what the masses of these objects are.
Okay, thank you again for the speaker.
Thank you.
Let's do 10 minutes.
Right.
Okay, thank you again. For next speaker today is Nestor Espinoza, talking about exoplanet characterization and synergy between JWST and Roman. So
Right.
10 minutes.
Yep, thank you. Well, super excited to be here sharing some of this science. This excellent preamble talk by Sam was great because I don't have to explain the whole detail. Now you're exoplanet experts, so I can just get to business. So what I'm trying to convince you in these next 10 minutes is that the synergy between JWST and Roman is not only on the science itself, but actually targets might pass from one side to the other, which I think is pretty exciting. So you know this number, you already heard it. Today we know about 5,000 exoplanets. That's going to be old news in 10 more years. 10 more years, you're going to have in the order of 100,000. That's a lot of planets. I don't know how we're going to create all that. I'm going to leave that to my colleagues. But I do want to focus on these planets that are going to be confirmed. So once you get these 100,000 planets, you're going to have an opportunity to characterize them in detail. And I think that's pretty exciting. One important fact about this number, as Sam already pointed out, is that most of these exoplanets are going to be transiting, actually. maybe for some of you in this crowd might be a surprise, but that's the deal. Most of them will be transiting exoplanets. And transiting exoplanets offer a ton of opportunities for characterizing the atmospheres of these worlds. I'm going to start with transits. You already saw from Sam a beautiful plot that was obtained by JWST, this fact that when planets transit, if you observe that transit at different wavelengths, then at certain wavelengths you will observe that the planet is larger or the transit is deeper. And that's because there's something absorbing in the atmosphere, right? And if you plot all these wavelengths, all the transit depths as a function of wavelength, you get this beautiful JWST spectra that Sam already highlighted. Which you're seeing a ton of details. This is going to be the standard now, and I'm pretty envious of the people that are like being born in the exoplanet field right now. This is what they get to see every day. And we're discovering that exoplanets are much more complex than we previously thought. This thing about photochemistry, this size of the features are a bit different than what some people were expecting. And this highlights the fact that we need to look. We need to keep looking at these features in these atmospheres. Now, how does this link with Roman? In the Galactic bulge time domain survey, Roman is expected to at least observe in 2 bands. Most of the observations are going to happen on the F147, 1.46 microns, with like a 1 micron band more or less. And another one will be the F087, like 0.87 microns. And as you can see here, the Roman F146 marks all the water features. You see all these water features that you're seeing here, the transits that Roman is going to observe are going to happen on those wavelengths. In this F87, Roman is going to observe some sort of continuum. So in theory, you should be able to observe this little delta blip on the transit depth if you observe one wavelength with the other. Let me show you an example. So what I'm trying to convince you here is that Roman is going to do this neat thing that it's going to be able to do transit spectrophotometry for like tens of thousands of exoplanets, which is super exciting. That's a data set that we didn't have in the past. So here I'm showing you the same similar WASP-39 spectrum that I just showed you before, but it's just a model, right? You see these blips here, this is just water. And these 2 points mark these 2 bands from Roman. So you see that one is larger than the other, just because of these water features here. The sizes of this feature change depending on how cloudy the exoplanet is. If it is very cloudy, then the 2 bands will be, transit depths of these 2 bands will be very similar. If the planet has no clouds, then the 2 will be very, very different. See that these 2, for example, is for no clouds on the planet, basically huge transit depth change. While it's going to be very difficult for Roman to just detect this blip in one planet, Roman can play by the numbers. Roman is going to have enough planets on the same radius temperature band that you will be able to bin planets together and form population properties of these worlds. Here's a simulated example of like just binning 30 planets of these tens of thousands that I just mentioned. At like a magnitude 17, you will be able to detect this water feature in that little population with just the transit depths. How cool is that? The incredible thing is that for the brightest of the brightest targets that Roman is going to discover, you could, in theory, follow up with transit spectroscopy with JWST. At magnitude of J equals 16, it's pretty faint, seems pretty faint, and that's on the bright end for Roman. But just like single transit, you could get like these beautiful features that you were seeing before from water and CO2. So my call here is for the Roman folks that are working on getting that sweet, sweet, bright photometry, precise bright photometry for the saturated stars. We really want them. They would be pretty awesome because we can actually link these 2 missions and follow up these very special planets that Roman is going to be discovering. Okay, so transiting planets offer you transits, but also they offer you eclipses. That's when the planets pass behind us. And that's a pretty exciting feature too, because as I just told you, the main band of the Roman Galactic bulge time domain survey, it's going to be this 1 to 2 micron band. And we don't have a lot of 1 to 2 micron eclipses out there. The only people getting those eclipses come from the ground. And they basically exhausted all the targets. They're like 20 brightest targets. They have exhausted all those targets. But now you have Roman that's going to enable you to get eclipses for thousands of those planets out there. So that enables a new science path. What can you do with eclipses? Well, this is called emerging results from JWST. Let me show you one result on emission spectroscopy from Roman18b. that JWST got a month ago, basically. So you can get basically the same thing as I just showed you, molecular features, but from the day side of the planets. And that's very different to the transiting, where you're looking at the terminary region. You can think of it as the morning and the evening of the planets. Here you're looking at the day side. Not only that, but if you have a well-sampled eclipse, you can actually study the light curve of the eclipse. And that can tell you how distributed the light is around that day side. If the eclipse is very sharp, then that means that the day side is very homogeneous. But if the eclipse has some sort of curvature, then that means that the planet day side is a little bit, diffuminated. And that tells you something about the atmosphere of the planet. So studying this is called eclipse mapping, can actually tell you, kind of the 3D properties of the day side, which is pretty cool. Here's a simulation that we did on a simulated phase curve for an H17 planet on a 4-day orbit. You see the transients here and the edges. I'm focusing here in the little eclipse. It seems small, but if I do a close-up, you can actually see how beautiful this looks like. It's not only the blip that happens when the planet passes behind the star, which is basically you're detecting these infrared photons from the planet. But the fact that the flux of the planet goes up, that's because you're seeing the faces of the planet. Just as we see the faces of the moon, we can do the same with the faces of these exoplanets. And we can do this for thousands of worlds out there that Roman is going to enable us to unlock. Did I mention already it's 1,000? That's more than 1,000. That's a factor of 1,000. That's in the order of 200, factor of 200 more eclipses from 1 to 2 microns that we have right now. Basically don't have kind of sections. And from space, we definitely don't have these wavelengths. Spitzer got in the order of like 400 eclipses in the 4 to 5 micron band, but that little snitch between 1 and 2 microns, we don't. But Roman is going to get you that. It's pretty exciting. Also, in these so-called phase curves, when the flux is going up, this doesn't have to be centered around the time of secondary eclipse. It can move a little bit, depending on the 3D nature of the atmospheric circulation of the planets. And that might shift, and that phase shift also tells you information about the 3D nature of these exoplanets. We will be able to get this with this Roman data. So what can you get from eclipses? It's not only the numbers. It's not just that this number sounds nice. You can get a lot of constraints on these planets. First of all, you can get eccentricity constraints. The time of secondary eclipse depends on the eccentricity of the orbit, on the actual 3D of the orbit. And you can get that information on the secondary eclipse. You can get atmospheric redistribution properties. If this phase shift, for example, happens for a certain population of planets and not for others, then that means that something is happening on this 3D circulation of these worlds. And you can get also variability studies. People have been claiming this for a little while now with the TESS mission, in which you have long baselines, in which you can see many phase curves, that it might be that this phase peak offset actually changes in time, perhaps. Now you're going to have thousands of worlds to explore that same thing on this very nice baseline that Roman will get you. So, to conclude on everything that I'm trying to tell you, summary. First, these emerging results from JWST are definitely motivating new frontiers in exoplanet science, in particular for transiting exoplanets. Roman is going to get you that. And in terms of exoplanet characteristics, it's in its numbers. The fact that Roman is going to observe so many stars is going to get you so many transiting exoplanets. Fraction of that you can characterize their atmospheres in these infrared wavelengths. It can help reveal relationships in atmospheric properties with the large sample statistics, and that other missions might not achieve because they don't have numbers. Roman has the numbers. And finally, Roman and JWST might actually be synergistic and complementary, not only in science cases, but actual observations of bright targets. So getting precise photography of bright stellar objects with Roman has huge potential. So if you're working on these, please keep doing that amazing work. Thank you.
You have questions in the room? Do we have any?
I'll ask.
Yep. Okay.
You talked a lot about atmospheres, but not about the surface composition and thermal inertia. And so what's the expected amount of exoplanets that you could do this sort of study with and gain atmosphericless exoplanets?
That's an excellent question. And this actually was tried with Kepler. But Kepler didn't have the numbers that Roman's going to have, so I'm happy you asked this. So while for the smallest planets, the Roman precision on a single planet wouldn't be enough to detect the eclipse, you can stack the eclipses from different small worlds and try to form like a super eclipse out of them. Again, this was tried with Kepler, but the wavelengths that Kepler was looking at, which was more on the optical, made it very hard. Roman has two things in its favor. Wavelength, 1 to 2 microns, where the emerging flux is going up, and numbers. You're going to have a ton, like tens of thousands of exoplanets on those, for those small exoplanets that you can actually, scale and compile this super eclipse depth of all the planets together. Right? You can stack those Likers and form like a super Liker. So yes, that's science that you can expect from Roman 2. So thanks for asking.
We have questions online? Other questions in the room? A quick question. So what is the minimum radius that would be in the discovery space? Roman?
Yeah, for this atmospheric characterization, in theory, you could go, a little bit above Neptune in terms of the secondary eclipses alone, like making single detections. But again, stacking, you can go even smaller. Yeah.
Okay, if there are no other questions, thanks again, the speaker.
Thank you.
Hello, can you hear me? No, just wait the version 3.
Ready?
Yeah.
Okay, so the next speaker is Julien Girard, speaking about finding exoplanet with Roman and JWST.
Yeah, good afternoon. I hope you're not sleeping. I know that a lot of you are not exoplanet experts, and it's going to be hard for me to have the same amount of energy as Nestor and Sam. So now I'm going to talk about finding exoplanets, and mainly with the direct imaging technique, because the other techniques have been mostly covered. So by now you know that we have found a lot of planets, mostly with transiting and radial velocity approaches, and they are everywhere. And they have different type of compositions that represent more or less the ones we have in the solar system, but not just. As Sam explained, there are planets that are a little bit bigger than Earth. We don't have that in our solar system. And also in direct imaging, we find big Jupiters that we also don't have in our solar system. So the different techniques, by now you know most of them, and several have been described already. I'm going to focus on those two, and mainly the one in the middle, the direct imaging, which is also called high contrast imaging. And one of the big advantages of it is that you detect directly the photons of the planet. And in this case, for example, the HRIT 799 system with 4 big young Jupiters, it's a little bit of a scaled up version of our solar system. You can actually see them moving with different epochs. This is Keck data, but we can observe those planets with JWST as well, except the data is not public yet. And then the astrometry is basically looking at the wobble of the star due to the presence of a planet, and this has been made even more popular with the Gaia mission, which I will show informs direct imaging campaigns and surveys. So this is a figure that was just crafted today by Tyler Desjardins, and I've been asking for it because I couldn't find it. Where is the coronagraph instrument field of view with respect to the huge wide field instrument field of view in the focal plane of Roman. So you see all the detectors of the wide field instruments, and that would be the size of the moon, right? And this little blue dot here, that's the detector of the coronagraph instrument, which is a technology demonstrator. Its aim is to show that you can do wavefront control in space, that you can do you can fly electron multiplying CCDs as a detector, and also that you can reach a contrast that allows you to do a giant planet in reflected light. So just like you see Jupiter in the night sky, but on around other stars. And that's for real, you know. That's the coronagraph instrument in the clean room as we speak. The focal plane masks and some pupil elements here, Leo stops. Not going to put too much details. You've seen this several times, especially with Sam before. So what we've been able to image directly so far are the green dots, and of course there are large separation planets, and so far they are young planets, around 1 to 10, 15 Jupiter masses. So they are basically big Jupiters. If we wanted to tackle a mature Jupiter, we don't have the sensitivity even with JWST. With JWST, we can go down a little bit in contrast at large separations, and sorry, I'm just going to move on. Yeah, so we're going to keep doing this with ground-based facilities. With JWST at large separation, we're going to be able to go down in mass, also see colder planets. With ground-based 30 to 40 meter telescopes in constructions, we are going to tackle this parameter space, and then the Roman coronagraph will be here, basically trying to find also Jupiter mass or maybe down to Neptune mass planets in reflected light in the visible. And then, of course, the hub worlds or more speculative observatories that I hope to see in my career. Anyway, so from the ground, there are surveys that have been done. A few hundred stars, like nearby, young stars have been observed. A lot of disks have been found, and in some cases, I would say a handful of cases, we found some planetary mass objects, and so we can basically draw detectability diagrams like this, like a kind of finger or thumb diagram. I don't know how you call it. But this is kind of over. With JWST and the Roman coronagraph, we don't have enough time. It's very time consuming to dig a contrast, a high contrast observation, and so we cannot go fishing, quote unquote, like that. So we have to go after informed targets. So it's a bit more like fly fishing. You know, you see the fish, you try to get it, and the information you get it from Gaia in astrometry. So you know there is a trend, you know. Anomaly in proper motion, so you know there is a planet, and also from radial velocity with large time baselines. So there are different number of works that have been done like that. Beta Pix C was found this way with radial velocity and Gaia, and in the gravity interferometer was able to basically detect its photons, and also AF LEP was detected like that. So to put it simply, this is what we can do today. Young giants in emitted thermal light from ground and space, and also sometimes in the visible in H-alpha when they are actually accreting, very young. For the first time, JWST allowed us to image an exoplanet above 5 micron with the MIRI instrument. So before 2030, with the Roman coronagraph, we should be able to do Jupiter analogs, so more mature systems in reflected light, maybe down to Neptune's. And then, so there's a tech demo. It's not that much time, and if it works, hopefully there will be a general observer program. And then beyond 2040, hopefully we'll have a bigger mission like the Habitable Worlds Observatory mentioned not so long ago by NASA. So that's going to be also reflected light in the optical, and the goal here is to go after a few, hopefully a few tens of Earth-like planets and super-Earths, also with spectroscopic capability. And our colleagues in Europe, especially in Zurich, are leading an effort to study an interferometer that would do the same type of planets, but in thermal mid-infrared wavelengths. So this is basically the roadmap. This is how the data looks like. So the one on the left is actually the real data from JWST on this planet that has just been renamed by the IAU and the community. In the middle, it's a simulation from Neil Zimmerman here sitting in the conference. It's an example of how the data is going to look like on the small field of view of the Roman coronagraph. And in this case, you have two planets in reflected light, about 1 Jupiter mass each. And on the right is what hopefully a 10 to 15 meter, maybe not a 6 to 15 meter telescope, segmented telescope would see if it is to fly in the future, and have a contrast of about 10 to the minus 10. So the way it works on JWST, this is NIRCam. This is a simulation pre-flight. When the mask actually is put in front of the star, you get an attenuation, that's the middle pane. But then it's actually not enough to see planets. To see planets like Jupiter, you basically have to subtract a separate star. So that's called reference differential imaging. And on Sky, it works very well. So this was a white dwarf that we did in commissioning just to mimic a planet, about 10,000 contrast at 0.5 arc second, works very well. We got some nice contrast curve. And so a few days later, in July last year, we got those actually 6 wavelengths with 2 instruments, NIRCam and MIRI, of this new planet. It's not a new planet, sorry. It was discovered in 2017, but it's the first time from space that it is imaged. And so JWST has a bit of a beam size issue. You know, it's not that big, and the wavelength is bigger. So if you were to go after HR8799, that's how it would look with NIRCam. In fact, it's been done, but I cannot show you today. It's tremendously sensitive and stable, but the beam size is a little bit big. And yeah, I'm gonna stop here because I'm running out of time. But this is super exciting. The Roman coronagraph instrument is basically a stepping stone to go beyond with a big telescope like HWO. And it's our best shot as a community to get planets in reflected light by the end of this decade. Thank you.
Thank you, speaker. Okay, do we have questions from the audience? What is it that you expect as if you would like to have a surprise from Roman? What?
Okay, a surprise from Roman. Okay, maybe I'm going to show a few slides. Okay. So the expectation from the Roman coronagraph is, so there's a requirement that has been relaxed because it's a tech demo, it's a technology demonstrator. So the requirements actually, we know it's actually pretty easy to achieve with respect to the hardware we have. Of course, everything has to go fine, and you know, the wavefront control. So you basically have deformable mirrors that are controlled with calculations that are made on the ground and sent to the spacecraft. So everything has to be very stable. But if everything works well, this is the requirement, but the prediction is more here. And so if it's here, maybe instead of doing, you know, giant planets like Jupiter, we can go down a little bit in mass, and that would be wonderful. I'm not talking about it here because I said it was finding planets, but it's also going to go after a few disks. One problem we have, so with JWST, our problem is that we have a ton of background galaxies popping out and photobombing our scenes, even in coronagraphy. With Roman coronagraph, it's the exozodiacal dust that's going to photobomb our scene, and might be, in some case, actually a bad surprise. But yeah, you know, between now and then, hopefully, Gaia is going to keep on being analyzed and released. The data is going to be released, and we'll have some really good candidates very nearby. So let's say at 10 parsecs, and they have to be pretty bright stars, around 5 for the wavefront control to work. Hopefully, we can. A good surprise would be to go to 10 to the minus 9.
Question over there. Oh, okay. Yeah, also one over there. In the meantime, maybe you can start with the online question.
Lasata Tulatar? That's how you pronounce it. You can ask it, sure.
I have a question online. I'm Mark Elowitz. Why is there no plans for like a star shade instead of a chronograph for Roman?
I think this is a little bit above my pay grade, maybe, but no. Well, I think, you know, maybe Dominic could answer better than me. We for the data challenge, so I didn't show many slides here, but we made a data challenge a few years ago where we simulated 4 epochs with the hybrid LEO chronograph, which is the one that will fly, and 2 epochs with a star shade rendezvous, which I think is still possible, but not decided, and maybe not likely. I don't know what. Yeah.
So the star shade was certainly an idea that floated around for a long time for Roman, but it became apparent at some point that a star shade was not going to be developed and ready in time for Roman's coronagraph to use it, because the coronagraph is not designed to be an instrument that necessarily will last the full lifetime of the rest of the mission. And so we have made choices that would make it extremely problematic to try to cooperate with a star shade at this point. So I hope that answers the question.
Yeah.
It could be added in the future, though.
In detail, to operate with a star shade, you don't merely have to have a dark thing floating out in space that you stare at. You actually have to coordinate the motions of those things. That requires hardware on both the Roman side and the star shade side. The hardware doesn't exist on the Roman side, so yes, it is possible, but somebody would have to go up there and service Roman to do it.
Okay.
Yeah, so that's very unlikely.
The question in the room.
Yeah, my question is there any prospect of direct imaging planets with a wide field? Because I'll be from very, very deep images.
Yeah, so in fact, I had this slide also. There is a way to have synergy between the two, I think. This has been studied by Melchior 2018, but also there is a mention of it in Tim Brandt's Astro 2020 white paper. So if you take a single epoch on a bright star with the wide field instrument and do exquisite astrometry using all the diffraction spikes, then you may reach maybe a single epoch precision of something like 50 microarc seconds. And that would be very useful to anchor and extend the Gaia acceleration measurements beyond the mission lifetime of Gaia. Also get more of those informed targets. That's what Tim Brandt showed in his paper, which would be suitable for the coronagraph and also other high contrast imagers. And also, you know, you could use those priors to do a better job at orbital fitting and properties characterization of those planets. So in fact, that was my conclusion, where, you know, JWST expands the parameter space towards thermal light imaging, cooler, less massive planets, large exploration. The Roman coronagraph introduces a new contrast regime, giant planet in reflected light. That's the main thing, the main demonstration. And both of those benefit from informed exoplanetary systems, and there is a synergy between the two eventually.
Very quickly, if you want to read the...
The question is Roman the first major mission to utilize a coronagraph in this way?
It's the first space mission that will have deformable mirrors on board, so that perform wavefront control in space. So because, like on the ground, we do adaptive optics to correct for the Earth's atmosphere and get basically what we call extreme adaptive optics, a diffraction limited beam, basically, from which you can separate the star and the planet. In space, you can go a factor 1,000 or so better. And the deformable mirrors, this time they don't correct the atmosphere. They correct the little defects of all the optics. And also the spacecraft has a bit of heat transfer happening. So you need to basically be stable over hours and correcting the optics over hours.
Thanks again, the speaker. The next speaker is Pedro Henrique Soares da Silva de Pinhon Nogueira.
Press the bottom, it's gonna work. And there's a pointer. Okay. So how I cursor works. Okay. 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 So let me just yeah, okay. Need to press. Okay, it's on. Okay. Thank you, everyone, for this opportunity to present my work as a talk. I am a PhD student in the last year, which means that in the end of the year I will be hunting for postdocs. So yeah, I work at Diego Portales in Chile, and I'm gonna tell you about what my group is doing about systems characterization, and more in particular to Eta Tel system. So thanks to Julien, I don't need to spend too much time on that slide, because it's basically we are using high contrast imaging, and you can see in the plot that the green circles shows the planets that has been detected with direct imaging, which are massive, and we can extend to larger separations from the primary sources than other planetary detection techniques. Well, with high contrast imaging, we have observed some interesting objects and systems. For example, we have observed planets forming, not just with direct imaging, but allied with ALMA observations and a lot of things. But we can see planets forming. We also have this GIF that Julien presented and of AGR 8799. So we have detected multiple planets in a singular system, and we also have detected triple systems composed by a central star and two substellar objects. So combining all of that with what we know about the moons in solar system, formed in situ, of course, we can imagine, okay, so if we are observing a primary source like a very bright star, and a companion that is a substellar object, can be a brown dwarf, can be a planet, it is possible to find something surrounding this companion The answer is theoretically yes, but it's hard to find it because we need to suppress not just the light from the primary source, but also the companion. So it's very challenging in the post-processing and also in the instrumental part. But still a collaborator of us have used a sample of 27 objects with a sphere that is an instrument in land, and the better fitted for this. And she used an algorithm that creates a model based on the instrument's response, and subtracted that from the observation. With that, we can obtain residuals, some sort of, if there is something, some sort of, let's say, let's not use the word exome because it can be contradictory, but it can be a satellite or a disk or a CPD, a circumplanetary disk forming. So in that sample, she found the first satellite candidate that is around the Eta Tel B. Okay. So we have ongoing survey with a sphere also that are using star hopping. So basically, just briefly, it will give us more models within time that will improve our subtraction. So we have ongoing survey. They started observation, I think, 3 days ago. So we don't have the data yet. But with that, we can go deeper, trying to find something surrounding companions. And we started our work now focusing on Eta Tel system because of several reasons. One of that is like a very young system, 24 million years, at the point that the primary source, the brightest star, has still a debris disk. And Eta Tel B, you can see down, that is a brown dwarf, a very massive one, which is good because it's bright. So we can detect like and it's well separated from the star, so it's not polluted by the speckles and the mask of the system. And we can see what we obtained with the old sphere observation, that we cannot see really nothing in the residual because we need deeper contrast. So another reason why we are starting with Eta Tel is because there is plenty of data, plenty of astrometrical data. So this table has all the published data with the positions. Here I'm showing separation and position angle until now, but this table doesn't contain 3 points using NACO, and it doesn't have our ongoing survey that we will add one more point. So we have a lot of astrometric coverage that we can do orbital fitting and follow up. On the right, you can see the contrast curves obtained by the oldest sphere observation. And we will improve that with a deeper observation with a sphere. You may be thinking why I'm talking about an instrument that is not Grace Roman. It's because we are doing the maximum to the land observations. But we are aiming to go for spatial telescopes also. Well, with the astrometrical coverage, we can do orbital fitting. This is preliminary results using Orvara. With Orvara, we can see the evolution in time from position angle and separation. We also can predict the location of the companion in the random time you specify. And also Orvara allows the RV data, radio velocity data, which we don't have for Eta Tel B until the moment. But we have we have the data, the RV data for queries pointing towards the companion, and we also have ongoing survey with queries plus on the data that tells us that is the first radial velocity into a companion. So we are working on that also. And with RV data, we can monitoring to look for satellites, which I mean, we can see an example here, use it for AGR 8799. So our ongoing survey with Queries Plus, we have just one epoch, but we will possibly obtain all the epochs that we requested, that are 15 until the end of the year. So with the RV diagnosis, we can see if something is perturbing the planet. In the bottom middle plot, we can see what would be the expected RV signal for Eta Tel B. And we have preliminary results on the spectra, so we have the temperature of the companion. Well, summarizing, we are doing the update of astrometrical and orbital characterization of Eta Tel B that compiles more than 20 years of data. We are doing the first ever high resolution spectra of a direct imaging companion. We are doing the first satellite hunting around the source, and we are improving the contrast curve, not just from this object, but for other objects too in our sample. Well, so in this conference, I'm talking about a lot of sphere, but we are aiming to use spatial telescopes that are more suitable to the task. So we can see in this table here some specifications from James Webb, but in the right we can see a comparison of contrast of Grace Roman and with sphere. So in sphere, we typically reach 10 to the -5 to the -6 contrast, but with Grace Roman, we can improve up to 4 orders that. So it will be 4 orders of magnitude more sensible to find anything. So this is great, not just for Eta Tel, but for all people that it's interesting on trying to trace some sort of signal around brown dwarfs and giant planets. With that, we can update our astrometry and orbital characterization of these objects, and also improve contrast curves and exomoon satellites hunting depth. With my last slide, I just let you with the face of our team. So in the first row are the astronomers, in the second row are the data scientists working with us in the group called YAMS. So stay tuned for future publications of this team. Thank you.
Thank you. We don't have questions from online audience. What about the room? Is there anybody in the room that want to ask a question? You mentioned you're working also on other system too. So what is the size of the sample that?
So the first sample with sphere is 25 objects, but in the ongoing sphere survey with more depth, we are serving 15.
15. And what is these are all brown dwarf companions, or you can go how low in mass in this sample?
In the mass of the sample, I think it goes from the more massive exoplanets to brown dwarfs. So I'm not sure now, but the companions are big because you need something big also to find something.
Okay, you have a question over there?
This is probably a pretty basic question, but again, exoplanets aren't my thing. You mentioned the term exo can be problematic. Why is
No, exomoons. Because of firstly, we were using this word, but part of the community doesn't accept it too much because the candidate is 1 Jupiter mass. So when you think in a moon in solar system, you don't think like something big. We were just considering the mass ratio because in the brown dwarf and this Jupiter mass would be similar to a mass ratio of a moon here. But still, it's not the size and the mass of a moon, so it's a problematic term.
You have more questions? No, then thanks again, the speaker. So the next talk by Rosemary Pike is an online presentation. See here on the screen. Here.
That coming through?
Yes.
Awesome.
But we cannot yet see you on the big screen, so.
You can't? Okay. It looks to me like I'm sending video.
Should be okay, just on our side.
Okay.
You lost the cursor.
On this side. Need to move this window. See the mouse? Need to move it to that other screen. Seconds.
Just a second. Okay, I think we're ready.
Great.
So 10 minutes. I don't know if you can see the clock, but sorry. 25 minutes and then questions. Thank you.
Thanks. So I'm Rosemary Pike. I'm an astronomer at the Minor Planet Center in the Center for Astrophysics. And I'm going to be talking about solar system stuff. So discovery and characterization of small bodies in the solar system, taking a look at some JWST results and prospects for Roman. So it's a mix of unpublished and published results from JWST, and I just want to give special thanks to some of the JWST PIs who provided some plots and results for this talk. So to start off with, basically as a general overview, we have small bodies in the solar system which all formed in a disk. They evolved over a period of 4 gigayears through collisions and scattering and movement by giant planets. And all of that resulted in the small bodies that we see today. So there are a lot of different populations, and they have a couple of different characteristics that we study to try to understand all of these processes. So we can look at the size distribution of the current objects, how many big things versus how many small things. We look at the composition, what they're made of, their shapes, the dynamics and orbit distribution of the objects. The fundamental question we're trying to answer is, what do we see today, and how do we use that to learn about the formation of the solar system from small body characteristics? So I'm basically going to start in the inner solar system and work my way out with all of these small rocky bodies. And so just to make sure we're all on the same page, we start with sort of the near-Earth object population, which can be near-Earth asteroids, near-Earth comets. This is a near-Earth asteroid, Eros, which was visited by a spacecraft. And so these are objects that have orbits relatively near the Earth, as the name implies, and can even be potentially hazardous. So these could be possible impactors. And part of my job at the Minor Planet Center is to try to find, to help compute orbits, and for the people who find all of these possible near-Earth asteroids. So as we move outward, we have the asteroid belt, including dwarf planets in the asteroid belt, such as Ceres. And this is a pretty large population, which is pretty collisionally evolved due to various giant planet scattering. As we go farther out, we have the natural satellites of the giant planets. And the giant planets have two different types of satellites. They have regular satellites and irregular satellites. So this is a picture of Europa, which is a regular satellite. So these are sort of these larger bodies that kind of are in a disk, kind of like the disk that we have around our solar system with the planets. And then we have irregular satellites, which are thought to be captured. So a lot of these objects they're not they're high inclination, and they're much farther from the planet. And so they sample an entirely sort of different history of formation and evolution than the regular satellites. And as we move farther out, we get to the Kuiper Belt region, where we have objects like Pluto and Eris. This is an image of Pluto and Pluto's moons taken before the New Horizons encounter. And all of these objects form what we call either the Kuiper Belt or the trans-Neptunian objects. And this is out beyond Neptune's orbit. And this is where I typically focus my own research. And out beyond that, we have the Oort cloud. So the Oort cloud is the big spherical region, which is circularized by galactic tides. And there are no Oort cloud objects that we have actually observed in the Oort cloud. So the only way that we actually see Oort cloud objects is when they come in as comets. And often they come in as retrograde comets. So these comets have really different characteristics than comets that come from the Kuiper Belt, which evolve into more lower inclination orbits. So just in summary, we're looking at sort of all of these different properties of the small bodies today, and we try to use that to infer the history of the solar system in the formation and evolution. And so what do we specifically learn from small bodies using JWST? So to start in the inner solar system again, you may have seen some of the press releases related to DART, which was an impactor mission. It was an intentional crash into Dimorphos, which was a 190-meter object asteroid moonlet, which is in a double system with the larger object Didymos. And so when the impactor occurred, we saw a tight plume of material with wisps away from the center. And it was imaged with the NIRCam imager. So the idea with this impactor was to try to change the orbit, the orbital period of the moonlet, and that this could be well measured due to the series of mutual events between the primary and the secondary. This object was selected basically as a test of planetary defense systems. In the future, like if we have a future impactor, we know how hitting an object would actually change its orbital properties. So they found that the impact slowed the rotation of Dimorphos by about 33 minutes, which was more than they expected. So it was a really successful test. And one of the things that's going to be really exciting and forthcoming in the future is the NIRSpec data, MIRI data, which will provide a bunch of information about what the material actually was that was ejected. Because knowing what the material is composed of can help us understand the material strength of these near-Earth objects and how they might respond to impacts in general. So yeah, it's a very exciting near-Earth asteroid. I included some results here from serendipitous asteroid observations. So this is particularly relevant to Roman. Basically, this is a JWST mirror image taken for science case that was not asteroid related. But we get 2 asteroids in the frame, and you can see multiple positions of the asteroid moving in subtraction. And there are smaller asteroids detectable using MIRI than in sort of general asteroid surveys, certainly in these wavelengths. So one of these objects was known and one of these was not previously known. So there's going to be a huge serendipitous catalog of asteroids found both with JWST and then later with Roman, which provides the data that we need to calculate the large catalog of sizes and albedos and to make new discoveries. So as we move a little bit outward into the main asteroid belt, this is a main belt comet. So main belt comets are really unusual. So when we think about cometary activity, it's typically objects coming from the outer solar system, which possess lots of volatiles, and as they get heated by the sun, everything sublimates, and that causes these beautiful tails and lots of volatiles. But in the main belt region, we expect these objects to be pretty devoid of these volatiles because they've been in a much warmer place. So a lot of times it seems like the activity in this region is triggered by collisions, but it's also possible that these could be interlopers from the outer solar system that just look like they're currently main belt asteroids. So this particular object is Comet Reid, and it's plotted against Comet Hartley 2. So the blue line is Comet Hartley 2, and that is a pretty typical comet. And you can see what's really important is that with the blue spectra, we see both water ice and carbon dioxide in relatively similar proportion. And the ratio of water to carbon dioxide is often used to measure how many volatiles are in a comet. But when we look at this Comet Reid, we see water and no carbon dioxide whatsoever. So the way that this is interpreted is basically that this is not an interloper from a more distant orbit, or we would expect the preservation of carbon dioxide. This is the first ever detection of water emission in a main belt comet. While we've seen dust and activity, we've never detected water emission before James Webb. So this detection of water ice is really important for our understanding of what the actual asteroids are made of. So if there are a large number of asteroids that actually have subsurface water ice that is preserved long term, that would greatly change our understanding of how water ice is preserved in the inner solar system, and possibly even how water came to Earth. And so this is a really exciting discovery, and hopefully it will be followed by more spectra of other main belt comets, and we can also expect Roman to discover a good number of main belt comets, which can be targeted for follow-up with JWST, searching for these water and carbon dioxide emissions. And right. This is the plot of the carbon dioxide to water ratio for a lot of different comets. And so basically just want to reiterate here how unusual this main belt comet is compared to all of the other comets that we've seen. So basically it's this red dot on the, basically it's the red upper limit. There are no known comets that look like this. So these main belt comets are really, really exciting, and probably change how we understand the asteroid belt in general. So one of the other really interesting results has come from Enceladus. So this is one of the regular moons of Saturn, and it is found in basically a torus of water particles, which it is emitting itself from plumes. There was a large plume observed coming from Enceladus at cryogenic temperatures, and they found the outgassing rate was similar to Cassini, and The torus density is consistent with previous Herschel observations. So it really looks like basically the water production rate is relatively long-term stable from Enceladus. It's supporting this huge water ice ring, basically, around Saturn. And interestingly, even with the really good density of JWST, they only identify water ice, no carbon dioxide or carbon monoxide, methane. And they also found basically only water ice on the disk of Enceladus, where it was dominant in a crystalline water ice form. So previously they have found carbon dioxide on the surface, and the lack of detection is probably just a geometric effect because it's near the poles. But long-term monitoring of the surface of Enceladus and other moons can also help us understand the composition of a lot of the major planet moons. So now we're getting into the outer solar system and taking a look at centaurs. So the centaurs are the population of objects that are evolving from the trans-Neptunian object region into sort of the Jupiter family comet region. So these objects have orbits inward of, say, Neptune, but outward of Jupiter. And there's quite a range of different things that we see. And a lot of these objects actually have jets. Some of them have rings. And one of the ones with rings is Chiriclo. And so the rings were known before this occultation was observed from JWST, and you can see basically the near-cam imaging on the right. But we do fast cadence imaging and try to see how much of the starlight is blocked. So the occultation actually only went behind the rings and not behind the main body, which is why we see only those sort of two quick reductions in the light from the star. But there are two rings around Chiriclo. They are partially resolved in this occultation, which was in October of 2022. And there's going to be a lot of work in the future looking at this carefully to try to understand how the rings form and how long-term stable they are. So it's one of the things that most likely the rings are composed of particles that are water ice from the surface of Chiriclo, and then a dark material from debris from some body that collided with Chiriclo in the past. But of course, we don't expect the rings to persist forever. So it's a question of, are the rings uniformly thick all around Chiriclo, and what is the size of the particles, and what does that tell us about the frequency of impacts in the Kuiper Belt? So there's a lot of ongoing work here in trying to better understand how the outer solar system is currently evolving, and what causes these ring systems in in centaurs. So to try to look at to understand this a little better, here is actually the surface of Chiriclo, which is dominated by water ice signatures. So previous ground-based spectra of TNOs has really struggled to identify surface ice, partly because of the wavelength coverage and partly because these objects are quite faint. And then a lot of the features are reasonably broad. So on the left, there's some of the best Chiriclo spectra from the literature, and you can see, particularly in 2003, maybe there's hints of water ice, and also in DEFRA 2014, we can see hints of crystalline water ice in the spectra. But really, it's a real challenge to identify features in TNO spectra from the ground. But once we move up to JWST, you can see these really clear water ice absorption bands at a range in multiple positions along the spectra, and also that there's not a whole lot else in this object in particular. I'm about to show a whole bunch of small body surface spectra And you should keep in mind for all of them pretty much that most of the ground-based spectra that we've taken has been relatively featureless, with the exception of the really large dwarf planets. And then in the optical, we mostly just see like a featureless reddening line at varying degrees of slope. And there's not really a lot of absorption or emission. So as we move a little farther out from the centaurs, we get to the Neptune Trojans. So this is the one-to-one resonance with Neptune. And in the one-to-one resonance with Neptune, there's some very interesting, basically the sample of objects is very unusual. The objects, we usually refer to them based on their optical colors. So either neutral or red, and then red or very red, ultra red. And because all of these objects in the optical are red. But in the TNO region, we have a pretty good mix of sort of these two red and ultra red surfaces. But in the one-to-one Neptune resonance, there's only one known object that has this ultra red color. And so this is a project where they took spectra of most of the known Neptune Trojans and tried to compare the one particular ultra red object to the red objects, and to figure out how those compare to the trans-Neptunian objects. And so the fundamental question is, why does the distribution of surfaces in the Neptune Trojans look so different from what we see in the trans-Neptunian region? And so spectra is really going to be key for understanding these, whether the composition has evolved since the objects have come to the Trojan region, or whether this is basically just a sample size issue, or has to do with, say, the sizes of the objects, because the closer in the objects are, the smaller the detections are. So here you can see JWST near spectra, and the ultra red object has this kind of similar to the Triton Tholin, which is just an irradiated organic kind of model. And the red objects show a strong water ice feature and minimal reddening. So this is also pretty much what we see in the TNO region. So that analysis is ongoing, but it will be really exciting to see. It does look like they are similar to the TNOs, and it's just a kind of bit of an open question as to why the ratio of the populations is so different in the Neptune Trojan. So just for fun, here are some beautiful dwarf planet spectra. So this one is Eris, taken from JWST, and you can see nitrogen features as well as methane features, and a lot of these volatile ices that we don't see on smaller bodies. And here we have some dark objects. So Eris is the highest albedo object in the solar system. It has geometric albedo greater than 1. And then these are much darker objects, and so they look different. And you can see, as opposed to being dominated by nitrogen and methane, we have a bunch of organic material on the surface. Organics haven't really been detected this clearly from the ground, and in particular, it's been near impossible to identify what organic materials actually are on the surface of TNOs. So the modeling of what organic materials actually make up the spectrum is all still ongoing, but organics are clearly detected, as well as water and carbon dioxide. So this is a spectra from a mid-sized resonant object similar to Charon in size, and it was selected basically based on similarity to Charon because we have ground truth observations from New Horizons in the Pluto system. And the preliminary reduction of this object shows water ice, carbon dioxide, and carbon monoxide. And the detection of carbon monoxide of TNO in TNOs is really new to JWST. So a little bit low on time, but just to kind of summarize all of the sort of TNO surface modeling, we have a very large program, which was 96 hours, the DISCO project. And this targeted 59 TNOs to look at their spectra. And they're looking at all different types of TNO orbits in sort of the range of sizes that we typically already know. They find both crystalline and amorphous water ice, and they divide the objects into 4 groups. And the critical thing about these 4 groups is that they are based on the shape of the water ice absorption and the carbon dioxide absorption, and they correlate with the optical colors. So as analysis moves forward with this, I'm really hopeful that we'll be able to tie the optical colors to this to the volatile populations in the objects. So that's really interesting to see. People have been classifying TNOs based on their optical colors for a long time because that's what's available. But to see these really clear classifications based on volatile ices has been really exciting. So this is results from a TNO discovery survey, which is about 45 hours on JWST, looking at a pencil beam survey where they're trying to find moving objects. So on the left, you can see one of the images and then a stack, and then on the right, that's the image with the sources removed. And you can see there's that very faint little object right there that is a TNO. So that one is previously known. But this survey is expected to find about 30 cold classical TNOs with diameters down to about 10 kilometers. And that's much smaller than any previous survey to date. And that getting the number of objects down to small sizes really helps us understand how the outer solar system objects formed. So what was the formation mechanism for the outer solar system? And this is particularly relevant for Roman because this type of search is probably how we will find most of the objects that will be discovered in the Roman survey. So here I'm going to touch on some Roman stuff, Roman science cases. Sorry, I just have a few minutes, but we have a couple of really exciting things that we haven't been able to do from other facilities, some of which can be done through the general surveys, some of which may require additional surveys, PI kind of projects. But finding Earth Trojans is one of the things that's really hard to do from the Earth for geometric reasons. So these are at the Lagrange points of the Earth orbit and can actually be stable for the age of the solar system. And there are only 2 known, but we could actually discover hundreds of objects with the Roman telescope in the Trojan points. Another really exciting population that we could discover a lot of things in is the high inclination centaurs. So when we search for solar system objects, people tend to search along the ecliptic plane because that's where most of the objects are. So you find the most things if you look where the most things are. But we're biased then against finding these things that are off the ecliptic plane, and high inclination centaurs are dominated by the Oort cloud populations. So finding, say, incoming Oort cloud objects is something that would be really great to understand better. And so particularly the high latitude surveys should discover a lot of retrograde centaurs and other high inclination objects. These high inclination objects are also really sensitive to there being, say, additional masses in the outer solar system, be that an additional massive planet or additional disks, basically additional belts that might exist out beyond the Kuiper belt. Roman is also ideal for an irregular satellite search of the giant planets. So I mentioned briefly that irregular satellites are captured, and we can get a good idea of the size distribution of these distant populations by looking at the size distribution of these irregular satellites. So right now, the Hill spheres are only about 50% complete in terms of whether we know how many things are in them, and we could actually go to smaller sizes than previous surveys, down to about 5 kilometers or 11 kilometers, depending on whether you mean Uranus or Neptune. And you really only need, you need about 100 to 10 pointings, depending on which of the giant planets you're trying to fill the populated Hill sphere of. So it would be, the wide field of view gives us a really great way to try to find these irregular satellites. We also may discover a lot of comets and interstellar objects, finding possible interstellar objects as they pass through the field of view. That one is pretty straightforward. And then finding these quickly so that we can do follow-up characterization would be hugely impactful science. And my own personal favorite thing is the serendipitous discovery of TNOs, particularly in these wide field surveys. We'll get enhanced discoveries, in particular if an ecliptic spur is included in some of these high latitude wide field surveys, and if the broadband filter is used, because we will find smaller things. We also will get serendipitous characterization. So I've dropped up the Roman filters on the upper left there, and you can see that it covers some of the water ice, but also some of the optical, where, as we discussed previously, the optical colors are correlated with the surface type. So discovering a large number of TNOs, getting them in multiple bands, and then selecting which ones to follow up with detailed JWST spectroscopy would provide really excellent data set for better understanding the bulk TNO populations. And so, in summary, the JWST results for solar system bodies are just beginning, but the identification of different volatiles is providing a really great context for interpreting the surface data that we've been seeing for years. And we expect Roman to serendipitously characterize a large number of known objects, in addition to discovering lots of new small bodies in the solar system. Thank you.
Speaker? So we have time for one or two questions from the audience or online. Any question from the audience? I know that statistic is hard to do because we only know two, but how many interstellar objects would you hope to see?
Yeah, it's really hard to speculate, right? Because we found two, they were completely different. One of them was like a sort of typical what we'd expect of, like, say, a TNO that passed into our solar system, or like a comet, and then the other one looked completely different. One of the speculations is that it's nitrogen ice. Yeah, I would hate. Yeah, I guess I'm not really comfortable speculating, but I do think that it's not unreasonable to expect, you know, more than one per year, something like that. But there are so many different assumptions you can make, and then of course it depends on what wavelengths they're bright in as well, and whether they are active, right? So if it becomes active, we can detect things that are much smaller.
What about the number of estimated Earth Trojans? Care to speculate on that?
Yeah, so based on the current models, which again are based on two, we would expect that there could be hundreds that we would discover with Roman.
Okay, is there a last call for questions? Oh, there is one online. Okay.
BS asks, isn't it also possible that the spectroscopy of the TNOs depend on the topological defects? If so, how will improved area and wavelengths help?
So spectroscopy depending on, okay, so I guess the question is basically, are the surfaces the same at all faces, right? Is that, so when you get spectroscopy, obviously you're taking it of one region of the surface. In general, most TNOs don't show a huge amount of variability with the exception of some of the larger ones. Obviously, you know, when there's actual like surface activity, like Pluto, where you have like ice resurfacing and stuff, you do see pretty large changes in the surface composition. So yeah, it is complicated to interpret, say, photometry and spectroscopy taken at multiple different epochs. And often it can reflect changes in the surface at different periods of time. But overall, in general, most of the distant solar system objects have the same surface as they rotate, which is what we see in photometry. But there is a much smaller sample of really good spectroscopy than photometry. Let me know if that was not quite what you were looking for.
I don't see the chat from the. Okay. Okay. I think that was what I wanted. Is there any other question? If not, I would thank the speaker again. And before leave the room for the poster session, we do have one poster lightning presentation. But we don't have the name on here. Amélie Moulet? Aurélie Goulet.
Hi, can you hear me?
Oh, it's
okay,
alive.
Perfect. Okay.
Can you hear me fine?
Yes.
Okay.
Please go ahead.
Hi. Yeah, sure. Thank you for the opportunity. So I'm Ariel Moulet. I'm a staff scientist at the NORIO. And with a few colleagues at the North American ALMA Science Center, we put together this poster to remind people of how ALMA is a great instrument to follow up on detection of high-Z sources. So, you know, high-Z galaxies, AGNs, quasars. I put two plots there showing how the different atomic lines and ionized lines are detected for different Z across different bands of ALMA. And on the right, it's the CO lines, a different transition of CO lines that can be observed at different redshifts. So from these type of observations, one can get spectroscopic redshifts, metallicity, molecular compositions. Some outflows can be mapped. Of course, mass estimation and star formation rate estimation as well. And this poster is mostly to highlight that ALMA is currently undergoing a wideband sensitivity upgrade at all bands that will be completed in almost 10 years from now. But this has a direct impact on high-Z research because line sensitivity will increase by 50% at all bands and continuum sensitivity by 70 to 120%. So if you look at the poster, you will get a sense of what ALMA can do now, but by the time Roman is up, several of the bands will have been upgraded, and the detection sensitivity will be significantly better. So if you have any question or you want to explore how some millimeter observation could benefit your science case that is powered by Roman in particular, please don't hesitate to reach out on Slack. That's all I had.
Thank you. I think this was the only one. Do we have any announcement from the organizer? No, then please, thank you for being here today and enjoy the poster session now.
Yeah, I know it's not going to happen, but I don't need to record this. Record. Well, I'm recording now. I need to get there like now.
Oh, okay. I thought we had
You have to get there. Oh, I have to get this. Oh, wow. Yeah, I know the table and the TV.
Oh, I did have one question for you. So, I was thinking something I'm not talking about the yield. Like, what do you
Sorry?